Hello everyone, welcome to another Leetcode video. Today we're looking at the problem minimum number of flips to make binary grid palindromic 2. This was question 3 in a Biweekly Contest 136, and this was a very difficult one. If you saw my screencast, you probably saw that I could not solve this during the contest, but was able to figure it out after the fact. I just want to run through exactly how this problem works. So, it reads we're given an m by n binary matrix grid. A row or column is considered palindromic if its values read the same forward and backwards. We can flip any number of cells in the grid from 0 to 1 or 1 to 0. So what we want to do is return the minimum number of cells that need to be flipped to make all rows and columns palindromic, but we also have to have the total number of ones in this grid be divisible by 4. So let's look at this example here. So we'll start with 1, 0, 0, 0, 1, 0, 0, 0, 1. What we end up with is 1, 0, 1, 0, 0, 0, 1, 0, 1. So we see that this column and this row is palindromic, this column and this row is palindromic, this column and this row is palindromic, and also there are 4 ones in the grid, which means that the total number of ones in the grid is divisible by 4. So this is actually kind of a problem we have to approach in 2 phases. So let's look at an example and see exactly how we can do that. So let's say we're starting with this grid, and we have, let's say this will be our m and this will be our n. So we have 0, 1, 2, 3, 4 in m and 0, 1, 2, 3 in n, right? So what does it mean to be palindromic? Well, we know that to be a palindrome, it has to be the same forwards and backwards. So for example, 0, 0, 1, 0, 0 would be a palindrome, 1, 0, 0, 0, 1 would be a palindrome, etc. You get the idea. But we have to have this property for both our rows as well as our columns. So how do we achieve this, right? Well, we could maybe try checking and see, is this a palindrome? If not, we could find a way to make it a palindrome. Say we could change this to 0, right? So we'll have 0, 0, 0, 0, 0. And then, we could check this, say, okay, that's also a palindrome, so it works in this case. But then we'd have to, do this for every row and column. And then we'd have to also keep track of the number of ones that we currently have. So this is going to be way too inefficient, right? So how can we actually go about doing this? Well, let's kind of think, what if we were at this point 0, 0, right? What do we know about this point? Well, we know that for this row to be a palindrome, this spot 0 has to be the same as this spot 4, right? So we know that we don't know what's going on in the middle, but we know that for this to be a palindrome, and we're considering this point, we know its complement has to be over here, right? Similarly, we do the same thing for this column. We'll say, well, for this to be a palindrome, this down here, right, this has to be the same as this. Likewise, over here, we say, well, for this one to be a palindrome, right, and remember, this has to be a palindrome, this has to be a palindrome, so for all of these to be equal, right, this has to be the same as well, right? So kind of what we're doing is saying, this is a palindrome, but for this to be a palindrome, right, this has to be equal to this has to be equal to this, right? So what we're looking for is groups of 4. Right, and this is what we're going to do for phase 1 of this problem. What we're going to say is, all right, well, let's look at these 4 complementary points. And how do we get these? Let's say we're starting with our I and j, which is 0, 0. So from this point, we want to be able to find all the complementary points that we need to check. So to get from here to this top right value over here, we can keep our I the same. But what we have to do is we have to say, we're going to take our m value, we're going to take whatever our current j is, and remember j is which column we're on, minus 1, right? So this will be 5 minus 0 minus 1 equals 4. So our overall point will be 0, 4, which is this point here. Likewise, to get this one in the same column, well, we're going to keep our j the same, right? So we know that our j here is going to be 0 for the 0th column. We can do something very similar where we take our n value, we're going to subtract our I, right, our row, and then we're going to do minus 1. So this is going to be 4 minus 0 minus 1. So this point overall becomes 3, 0. So 0, 1, 2, 3, 0. And likewise for this last point, what we're going to do is we're going to not keep either the column or the row the same. So what we're going to do is we're going to take, first to get our row, we're going to do n minus I minus 1. And to get our column, we'll do m minus j minus 1, right? And this will get us 0, 1, 2, 3, 4, right? So we're going to use these equations in order to get all these complementary points. And this will work for any point that is not in a middle column, right? And middle columns can only happen when we have an odd number. So you see here, we have 4 rows, right? So there's not really any middle. Our middle would be right through here. But for our columns, right, we do have this middle here because we have an odd number. So there's 2 on the left, 2 on the right. And we're going to handle this case later. So essentially what we're going to do is we're going to go through each pair, and we're going to go to n minus 2 and m minus 2, right? Because we only need to go through half of these. So let's see what this actually looks like. So we're going to start at 0 and go to n over 2. And we're going to say, okay, let's get this point, get all our complements. So we see 0, 0, 0, and 1. So we have 3 zeros, and we have 1, 1. So in this case, what do we want to do? Well, it makes more sense to just convert this 1 to a 0, right? Because in one move, we can now have all 4 of these be the same. So we could say here, we want to have 1 move. Then we'll move to the next one. So what we can do is say, we're going to get all the complements. We have 0, 1, 1, 0. Here, it's the same. We have 2 1s and 2 zeros, so we can go either way. So let's say either way I have to do 2 moves. Then what's going to happen is we're going to get to here. And we're only going to n over 2, so what we do is we'll go down to the next one. And we'll do the same thing here. So we can do the complements and just get our score. So this is the first phase. Let's call this phase 1. But however, you'll notice that since we're only going to n over 2, we never process this middle, right? So how are we going to handle this case? So phase 2 is where we're going to handle our middle row and middle column if we have them. So what we're actually going to do is we're going to count pairs. So we're going to treat this, like we would a regular palindrome. So we're going to have 2 pointers, one starting here, one starting here, and we're basically going to count 2 things. We're going to count the number of 1 pairs, right? So these are pairs where both of the elements, so say this was 1 and this was 1, where both of these are 1. We're also going to count where there are mismatches. So here we would have 0 and 1. This would be number of mismatches. So what are we actually going to do with this? Well, what we can do is say, if we have 1 pair, right? What does this mean? Well, if we have 1 pair, that means there are 2 elements in there. So it means we'll have 2 1s essentially, right? If we have 2 pairs times 2, we would have 4 1s. So what we can do with this is we can check at the end if the number of pairs is odd. And if it's odd, this means that we'll have 2 1s, or for example, like 6 1s, right? We don't have a number divisible by 4. But if we have an even number, it means that we have seen an even number or a number divisible by 4, so we don't have to do any other work here. So what do you do with these mismatch pairs? So you can imagine that if we do have an even number, right? Say we have a row like this. So we have 1, 1, these are a match, 1, 1, these are a match, but then we have 0, 1, right? So we see that these pairs are matched right here. These pairs are matched. We just have these ones left, right? So what we can do is we can just change either one. We can just change this to a 0. We can change this to a 1. It doesn't really matter. But essentially, if we have an even number of 1 pairs, then what we do is say, we just need to convert the rest of these to be either 0s or 1s, right? Because then we can make them all equal. In this case, we probably convert it to a 0 so we can have an even number, right? So if we had 0, 0, 1, we just get rid of the 0 essentially. But really the cost to change it is the same whether we change it to a 1, change it to a 0. What we're doing is saying we've matched enough pairs of 1s to make sure that the number of pairs is even. So all we have to do with the remaining pairs is just get rid of the 1 essentially. So, however, there's another case. What if we actually had an odd number of pairs, right? Well, in this case, what do we have to do? Well, we see that we have one pair here. So we have 2 ones currently. But what does this mean? Well, if we have other mismatching pairs, right, we can just update this 0 to a 1, and now we have 4. So essentially what we're going to do is say, if we have an even number of pairs, right, if it's even, we can basically just use those mismatched pairs and just get rid of the ones and have, make sure we have all zeros for the remainder. If we have an odd number of pairs, then we can change the zeros to ones if we have mismatches. There's also the case where, say, we just have this, right? We don't have any mismatched pairs. Here, so for example here, what we'd have to do is we'd have to just update both of these to 1 in order to make the number divisible by 4. So there are really 3 cases to consider. So if we have an even number of pairs, there are 2 ways this can happen. If we have an even number, it means we've already made the amount of pairs that we need to, right? We have 1 pair here, 1 pair here. So what this means is any of the mismatched pairs, we can just get rid of the ones and make them all zeros, and our cost will really just be that number of pairs. If we have an odd number of pairs, there are 2 ways it can go. So if we have an odd number of pairs, but we have mismatches, we can use those mismatches and convert the zeros to ones, like in this example here, to make the number of ones divisible by 4. However, if we don't have mismatched pairs, say we have 1, 1, and we have 0, 0, then we know here we have to change both, right? These both have to become ones because there's no other way that we could possibly get to a number divisible by 4. So there are a couple different test cases. You'll see how we handle those in the code. But overall, I think the logic here is much harder than the actual coding. There's kind of 2 different ways you have to go about this. You have to first match all the groups of 4, but then also handle the cases of middle columns and middle rows individually. But overall, we're only going through the matrix once, so overall we n times n time. So there's one other edge case we have to consider. So say we have a grid that has both an odd number of rows and an odd number of columns. And let's think about this middle point here. So is there any way that this can be a 1? So let's think about it. So we want the number of ones in this grid to be divisible by 4. But to make this column and this row a palindrome, you'll see that it is actually impossible for us to have that. So let's just try it out. So say we had 1, 1 here, right? Well, this is a palindrome, but this is not divisible by 4. We could maybe make a 1 here and a 1 here. I mean, these are all palindromes now, but still, we have 5 ones, not divisible by 4. So if you could try all the iterations of this, but you'll see that if we have an odd number of rows and an odd number of columns, the only way that we can ever get a number divisible by 4 is to make sure this center is always 0. So we do a special check as well, just to make sure that if we have an odd number of rows and odd number of columns, we do have a center point, and this always has to be 0. So the first thing we do is just grab m and n just for convenience. Then we set up our total swaps variable, which is what we're going to return at the end. So we're going to iterate through our grid, but we're only going to go to the halfway points of our columns and our rows. Then we grab those 4 points using the variables we outlined before, and whichever one is less, we're going to just go through and count them, and we're going to swap whichever one occurs least frequently. So then there's the condition of the middle point. So if we have an odd number of columns and rows, we have to make sure the center point of our matrix is always going to be 0. So if it's 1 in this case, this is where we want to just swap that. Then we're going to go through and do the logic of odd number of columns and not odd number of rows. So here we're checking for an odd number of rows. So if the number of rows is odd, we're just going to go through that row. And what we're going to do is we're going to count the differing pairs. So this is pairs where we have a 0 and a 1, and also 1 pairs where both of them are 1. And we do the same thing for our columns as well. So then at the end, this is where we do that logic for the three cases. So if the number of 1 pairs is divisible by 2, right? This means that we're going to return the total swaps we found so far, but we also need to convert those differing pairs, right? So this is the case where the number of pairs is even, so we don't have to change the number of ones, but whatever differing pairs that we have, we need to decrease those all to 0 and get rid of those differing pairs, right? And then this is the case where neither of those are true. So this is the case where the number of swaps, or rather the number of 1 pairs, is odd, but we don't have any other differing pairs in order to compensate for that. So we know we have to add 2 elements in order to get a number divisible by 4. So let's submit and make sure this works. And it does work. So this is a pretty hard problem, and there's a lot of different edge cases to consider. So hopefully this made sense and was helpful, and thank you for watching.